So moving on to the lecture, let's just study what are the structural differences between the two type of structures, statically determinate structure and indeterminate structure. I will be using this abbreviation SIS more frequently, so just try to get used to this one. Okay, as you know that in determinate structure, obviously there are two supports only. So obviously one can imagine that the stresses and deflections that will be developed in this type of structure will be large compared to the one in statically indeterminate structure, because in this one, for example, if this is a beam, this one is indeterminate beam. Obviously, it is indeterminate, but we have provided more supports, so it can resist more loads, and therefore the deflections are very small. So if we have two beams, this simply supported beam, the maximum moment that will be developed in this one is PL by 4, and the maximum moment developed in this fixed ended beam is PL by 8. So if we calculate the flexural stresses, which was by this formula, and if we apply this formula and calculate the flexural stress, obviously the moment is larger in this kind of simply supported beam. So the stresses that will be developed in these beams will be higher compared to this one. Here the moment is small, so obviously the flexural stresses or any kind of stresses will be small, and so it can resist the deflection in a better way compared to the indeterminate structure. So, another important thing is that can you please turn off your mic? And obviously, in indeterminate structure, we have to provide an extra support. So to build that support, for example, in the houses or in normal structures that we see every day, if this is a beam, then this type of support is provided, or the concrete is provided something like this in this way, and this is what we call as a fixed beam. And if we want to provide a simply supported beam, then the column is provided at the bottom only. So in this one, you can see that more concrete is provided, or so the cost obviously for this indeterminate structure exceeds. So we have to be very careful in while selecting the indeterminate structure. If the purpose is being fulfilled by the simply supported or by determinate structure, we should not go for the indeterminate structure. We should figure out the deflections that can, or the loads which can occur on the structure, and then we should see whether the determinate beam can resist those loads, or the deflection developed in the determinate beams or within the allowable limits. Then we should go for the determinate structures. If nothing works out, then only we should go for the indeterminate structures. And obviously you can imagine that the solution or analysis of these indeterminate structures is complicated compared to the determinate structures. And again, the point is same, that the internal stresses that are developed are very rare. This actually means that, for example, if this is a simply supported beam, and let's say this support is on the floor, and if this floor settles, then what will happen, that this beam will move something like this one, or deflect, like obviously this is very large deflection that I have shown, it doesn't deflect this much. So anyway, this beam will deflect something like this one. But if we have a fixed beam, let me show you here, it will be something like this one. If the settlement occurs in this type of beam, then what will happen when this part move up? Now this whole part is connected to this beam. So when this whole part is connected to this beam and it will try to move in the downward direction, the stresses that will be developed in this portion, or the force that this connection will be producing on this beam, will be very high compared to the one that will be produced in this one, because in this one it is not connected from each side, it is connected only from the bottom side. So the stresses that will be developed in the case of determinate structures are quite small compared to the indeterminate structure. So obviously this is not the main concern for us, this is just for the just to let you know about some theoretical differences. So these are some differences between these two structures. And another important point is compatibility conditions. Previously, we have studied the equilibrium condition that a structure should satisfy the equilibrium conditions, and we have three conditions. One is sigma fx is equal to 0, sigma fy is equal to 0, and sigma moment is equal to 0. These are the equilibrium conditions that we use to analyze the determinate structure. But since these conditions are not sufficient to analyze the indeterminate structure, so we have to look for other conditions, and those other conditions are the compatibility condition. So the basic definition for compatibility is that the displacement and rotation should be continuous throughout the structure and compatible with the natural support condition. For example, in this case, we should when we be plotting the elastic curve for these kind of beams, we should consider each type of support condition. For example, if we plot the elastic curve for this beam something like this one, this is wrong, because we know that natural support condition, we know that at fixed support, this deflection and the slope or rotation at this fixed support should be zero. That is why this elastic curve is passing through the center. And this concept that the deflection, can you please turn off your mic? So now these conditions, that is deflection is equal to 0, theta is equal to 0, and these conditions that at roller support there is some rotation, let's say some xy value for rotation. We have to use these conditions to write the compatibility equations, and based on these equations, we will figure out the four. For example, in this case, we need 4 equations. So based on these conditions, we will write the fourth equation and correlate it with the force or with the reaction. Let's say it is something like this one. And using this fourth equation, we will find this fourth reaction. And then once we have this fourth reaction, we will substitute into this equilibrium equation and we will figure out the other 3 reactions. So this fourth equation or this type of equation which is correlating the displacements and rotation with the deflection and or with the external force are known as compatibility conditions. But we have to be very sure while writing these, very careful while writing these conditions, because they depend on the support conditions and types of beam, and this I think you will get used to it once you solve different types of structures. And there is another concept of stiffness and flexibility, which you might have studied in basic mechanics course somewhere. So I will just review it briefly, that if you have a linearly elastic structure, and you apply the load, what will happen? The deflection will be produced, that I have denoted it over here by U. So whenever you apply the load on an elastic structure, the deflection will be produced, and when you leave that load or when you remove that force, that structure will go back to its original position until or unless you are within the elastic range or you obey the Hooke's law. So if you plot this force, you know that as you increase the force, the deflection will continue to increase and you will have this 45-degree line. Now what is stiffness? Stiffness is basically the slope of this linear line or the slope of force deflection relationship. Or if we define the stiffness can be defined as the force required for the unit deformation of the string of this spring. For example, if I write the equation of this stiffness, it will be something. If I want to find out this slope, that will be k is equal to p2 minus p1 over u2 minus u1, or I can write it that it is force per unit displacement, or I can also write it as p is equal to k2. So this is what the relationship of stiffness is, that the force required for the unit deformation of the string is known as stiffness, and its units are obviously the units of force per length. It can be pound per foot, pound, kilonewton per meter, or whatever the units are. And what is flexibility? Flexibility is basically simply the inverse of stiffness, and it is denoted by factor F. Stiffness is K, then F is equal to 1 over K, and we can also write that P, if I substitute this into this one, then we have P is equal to 1 over F into U, or I can write the equation for flexibility as U is equal to FP. So we have to use these terms in the analysis method, so that is why I'm just reviewing it briefly so you have these things in mind. So stiffness is the force per unit deflection, and flexibility is the inverse of stiffness. And one thing that both of these conditions are for elastic structures. If the structure goes beyond the elastic limit, then it can't come back to its original shape, and all the theories change. So any type of the beam structure or the frame structure that we have been solving, we are considering that all of our members are in the elastic limit or are in the elastic range. Now, if we have a simply supported beam, let's say this beam on which a unit load or any kind of point load is acting. Now, as a result of this load, there will be some deflection that will be produced. And while in these previous methods that we have studied, the Castigliano's theorem or moment area theorem, we have calculated or we have developed the formulations for the deflection. And for this simply supported beam, the formula for the calculation of deflection is this one, that is U is equal to PL cube over 48 EI. If I just simplify it briefly, or I move this P factor over here and just rearrange it, I will get this equation. P is equal to 48 EI over L cube into U. So can I say that this equation is equivalent to the equation of stiffness that we have just studied, that is P is equal to KU. So from this analogy, we can say that the stiffness of beam or this particular factor of 48 EI over L cube represent the stiffness of this simply supported beam on which the load is acting at the center. So this is the stiffness, and if I want to figure out the flexibility, it will be completely opposite to, or it will be the inverse of the stiffness, that is L cube over 48 EI. So actually when you were doing this conjugate beam method, or this moment area method, you were indirectly also calculating the stiffness of different type of structure. But back then we didn't discuss this, so you didn't realize it. Now, just by simple comparison, we figure out that what is the stiffness of beams of frame. So now you can say that you can also calculate the stiffness or flexibility of any type of a structure. So this was a brief review of what we have already studied. So let's just discuss briefly different methods. So the basic conditions that we need to satisfy during the analysis of indeterminate, this SIS is statically indeterminate structure, is that we need to satisfy this equilibrium condition, this compatibility condition, and force displacement conditions. I should write over here. Anyway, we have discussed that what are the equilibrium condition, how can we satisfy them, that sigma fx is equal to 0, fy is equal to 0, moment is equal to 0. We have to satisfy that, and the compatibility conditions we have to satisfy that, and by this we mean that the relationships, and by the way, this P is equal to KU. This is the compatibility equation. Now, if you see that in this equation, we have correlated this displacement with the force. So by using this relationship, we will, this basic relationship is the foundation of these methods that we will study for the analysis of indeterminate structure. So we have to satisfy this condition or this compatibility condition as well while we are analyzing these indeterminate structure. And again, the force displacement relationship is the same as we have studied for this spring structure, that the material should always remain in the elastic limit. It should not cross that. And our basic condition while deriving all these equilibrium condition or whatever was that our material was elastic. So we don't have to worry. We have already satisfied this condition while computing the deflections or rotations of the structure. So the first method that we are going to study is this force method, which is also known as compatibility method or method of consistent deformation. It was initially proposed by Maxwell in 1864, and then it was modified by Muller. Now this person was the same who developed the influence line diagram, and this Otto Mohr was same who developed the Mohr circle that we studied in the mechanics of structure course. So they have provided with this force method for the analysis of indeterminate structure. So let's start our discussion on this one. So let's suppose we have this beam with a fixed support at one end and a roller support at the other end. So if I see out, if I want to find out the degree of indeterminacy, that is 4 minus 3 is equal to 1, because we have 4 reaction and 3 equilibrium equations. So it is 1 degree indeterminate. So that means that in this beam we have one extra reaction that we need to figure out somehow. And if we can figure out this one extra reaction, we can simply solve this beam by using our equilibrium condition. So let's call this as our primary structure. Okay. So this force method basically says that if you remove this extra support, then what will you get? If I remove this one, this load is acting. I have removed this support, and I will get this shape, and when this load is acting on the beam, it will produce some kind of deflection in this beam. Let's call this deflection as delta B. If this point is A, this is B, then this deflection is delta B. Okay, and in the other structure, this method says that we should apply a redundant force at this particular joint or the reaction that we have removed. So the reaction at this particular joint will be By. And due to this reaction, now we will remove this load as well. There will be another deflection that will be produced in upward direction. Let's call this as delta dash B into B, right? Now, can I say that this particular beam or our primary structure is equivalent to this, let's call this structure as, in the book they usually call it as original structure. This is the primary structure and this is the redundant structure. So can I say over here that the deflection that is in our original structure is equal to the deflection in our primary structure plus the deflection in our redundant structure. Now what we have done basically is that in the initial beam, we have removed this roller support and allowed the structure to deflect. So what will happen? It will deflect in the downward direction. And in this beam, we have again applied this reaction or this roller support over here. And what will happen that it will produce an equal amount of deflection in the upward direction. So in the hindsight, this deflection will be equal and opposite to this one, so it will cancel out, and the final result is that there is zero deflection as in the case of our original structure. So we have just done this small practice to figure out one extra equation which can correlate this particular reaction force By with this deflection delta dash BB with the relation that we have just studied. So let's say if this deflection is delta B, and we have studied this relationship P is equal to K into U. So can anyone tell me that how can I relate this reaction force with this deflection delta dash B? Anyone?
Sir, could you repeat your question again?
How can I correlate these two forces, this deflection and this force? What is the deflection in original structure?
I'm sorry, what structure, sir?
Original structure, this one.
Uh,
Is there any deflection that I've shown over?
A roller sport or any?
I haven't shown any deflection over here, right? So there is a, let's say just call it as zero deflection, right? So now I have removed this roller support from this side or from right end, and we have this small deflection. So in this primary structure, we have this deflection delta B, right? And what is the deflection in this structure? Where I have again applied the reaction of this roller support. We have delta dash BB. But again, if you look into this figure, you can see that this deflection is in the downward direction and this deflection over here is in the upward direction. So we have to apply the negative sign with one of them, right? So this is our compatibility condition for this particular beam. Now what I did, I'm just going to repeat again that there was this beam, and this force method says that if you remove this force, remove this support, or remove any extra support for that matter. For example, in this case, we have removed this roller support just to make this beam determinate. Now after removing this roller support, this beam has become determinate. But again, when we remove this roller support, there will be some kind of a deflection that will occur in this beam due to the application of this particular load. So this deflection is known as delta B. And in the second case, because we have to make it equal to the original structure, what will we do? We will remove this applied load as well, but we will apply this external reaction By, and now only this external reaction is acting, so it will again produce some kind of deflection that we have represented by this factor delta dash BB. And if I write the equation for these three beam, or by principle of superposition, what will happen that this beam should be equal to the sum of these two beam, right? It should satisfy these two beams should satisfy the condition of the original beam. So what that means is that the deflection in the original structure there was no deflection, so that is equal to zero. And in the primary structure, we have deflection at the roller support due to the application of this P load that I have represented by delta B. And then in this redundant structure, or when I have applied the redundant load, there is another deflection delta dash BB in the direction of this applied load, and that is represented as delta dash BB, and this is what our compatibility condition is. And okay, we'll discuss that later. First, just focus on this one. Now, if you remember, just now we have studied one relationship, that is U is equal to FP, right? So U was basically the deflection, F was flexibility, and P was the load. And this particular load P was acting in the direction of displacement. Just when I have shown you the example of this spring, if you remember that load was being applied in this direction P, and the deflection was also being produced in the direction of this load, in the direction of this load P, right? So same is the case over here. This reaction By is acting at this right end, and due to this reaction By, this deflection delta dash Bb is being produced exactly in the direction of this reaction. So I can compare these two equations. So if I want to write this stiffness equation for the flexibility equation for this particular beam, can I write it as delta dash Bb is equal to F into this applied load will be equal to By. So if I replace this equation into this one, I have 0 is equal to minus delta B plus delta dash Bb is FBB and By. So again, if I rearrange this equation, what will I get? Because first I need to find out By. So I will get By is equal to delta B over FBB. So this is my equation for the calculation of this reaction. Now this is all about the theory of this force method. Now you can see that I have figured out one equation for the calculation of this reaction By, right? I have correlated this reaction with this deflection equation, with this deflection and this flexibility. Now, when you have studied the method, that conjugate beam method, moment area method, or double integration method to calculate this deflection B. For example, if I give you this beam on which this load P is acting, can you calculate this deflection delta B? Can you or can you not? Anyone? Arun, can you calculate this deflection? Class, do you remember what we have studied in the previous course?
नहीं सर, क्योंकि वो डिटर्मिनेंट के लिए नहीं थे सर.
What?
जो मेथड्स हमने पढ़े थे उनमें तो डिटर्मिनेंट स्ट्रक्चर्स थे सारे.
नहीं, ये स्ट्रक्चर डिटर्मिनेट है कि नहीं है? ये वाला
इनडिटर्मिनेट लग रहा है.
दिस वन.
हाँ सर, ये डिटर्मिनेट है.
डिटरमिनेट स्ट्रक्चर, राइट? ठीक है, इस पे एक लोड P लग रहा है. ठीक है, अगर मैं आपको कहूँ कि इस पॉइंट पे आपने डिफ्लेक्शन फाइंड करनी है, जिस B पॉइंट पे, तो आप फाइंड कर सकते हो या नहीं?
कर सकते हैं सर.
क्या होगी वो डिफ्लेक्शन? डेल्टा B होगी, दिस डेल्टा B. ठीक है, अब वो डिफ्लेक्शन आप इस इक्वेशन में सब्स्टिट्यूट करो. ठीक है, उसके बाद आपके पास आ जाती है फ्लेक्सिबिलिटी. फ्लेक्सिबिलिटी क्या होता है? अगेन वही केस है कि स्टिफनेस का ऑपोजिट होता है फ्लेक्सिबिलिटी. तो स्टिफनेस कैलकुलेट कर सकते हो, जस्ट जो मैंने आपको स्लाइड पे दिखाया था. फॉर एग्जांपल इन दिस स्लाइड आई हैव शोन यू दैट इफ यू हैव दिस बीम, तो आप उसी बीम की इक्वेशन लिखो लोड और रिफ्लेक्शन की फॉर्म में, एंड देन यू कैन फाइंड आउट द stiffness, and inverse of stiffness is flexibility, right? तो फ्लेक्सिबिलिटी भी आप कैलकुलेट कर सकते हो इन मेथड्स को यूज करके. और जब आपके पास ये दोनों फैक्टर आ जाएंगे, तो इन दोनों को आप इस इक्वेशन में सब्स्टिट्यूट करोगे, तो आपके पास डायरेक्टली ये रिएक्शन By आ जाएगा. अब मैं आपको ये बीम दूं अगर, ठीक है, और इस पे ये लोड P लग रहा हो, और आपको By पता लग जाए ये 10 है, ठीक है, इस पे लोड 20 लग रहा है, तो अब ये बाकी तीन रिएक्शंस फाइंड कर सकते हो. तीन तो नहीं होंगे, दो ही होंगे इसमें, तो ये दो रिएक्शंस फाइंड कर सकते हो. कैन यू? खिजर, हंसना.
Yes, sir.
Can you find out these two reactions?
सर आप दोबारा स्क्रीन दिखाएं एक सेकेंड.
Can you figure out these two reactions?
सर ये वाला फॉर्मूला यूज करके फ्लेक्सिबिलिटी का
कौन सा फार्मूला यूज करना चाहिए हमें? दिस इज द बीम, इस पे ये लोड लगता है,
डिटरमिनेट.
ये दो हमने फाइंड करनी है.
जी
कर सकते हैं फाइंड?
हाँ सर, ये तो हम सिंपली भी फाइंड कर सकते हैं.
कि कौन सी इक्वेशंस यूज करके?
रिएक्शन की
इक्विलिब्रियम इक्वेशंस.
इक्विलिब्रियम इक्वेशंस.
सिग्मा fy is equal to 0 और सिग्मा मोमेंट is equal to 0, राइट? सो आपने बेसिकली किया क्या इसमें कि आप कंपैटिबिलिटी कंडीशन यूज करके एक रिएक्शन फाइंड किया आपने, फिर आपने इक्विलिब्रियम कंडीशन यूज करके बाकी दो रिएक्शंस भी फाइंड कर लिए हैं, और फोर्स डिस्प्लेसमेंट रिलेशनशिप आपने यूज किया था इस जगह पे, और आपने जो ये डिफरेंशिएट किया था. सो ये तीनों कंडीशन सेटिस्फाई हो गई. जो ये तीन कंडीशंस थी कि हमने इक्विलिब्रियम कंडीशन भी सेटिस्फाई की है, कंपैटिबिलिटी कंडीशन भी सेटिस्फाई की है, और फोर्स डिस्प्लेसमेंट कंडीशन भी हमने सेटिस्फाई की है. एंड बाय सेटिस्फाइंग दीज थ्री इक्वेशंस वी कैन डू द एनालिसिस ऑफ इनडिटरमिनेट स्ट्रक्चर. सो दिस इज जस्ट अ बेसिक theoretical intro.
स्ट्रक्चर तो डिटरमिनेट था ना ऑलरेडी, जो आपने सेकेंड एग्जांपल कराई है.
कौन सा? ये
हाँ, जो सेकेंड एग्जांपल करवाई है.
this one I haven't. Which is the second example?
जो आपने डिटरमिनेट की करवाई.
This one.
यस.
ये एग्जांपल आई कहाँ से? ये 10 आपके पास कहाँ से आया? This 10 is basically by. I just gave you the example कि अगर आपको by इस इक्वेशन से पता लग जाए तो फिर आपके पास ये डिटरमिनेंट हो जाएगा. ये बेसिकली वही स्ट्रक्चर है, मैं इसी एग्जांपल की बात कर रहा हूँ. This one. इसमें आप by फाइंड कर रहे हो कंपैटिबिलिटी यूज करके, और बाकी दो रिएक्शंस आप फाइंड कर लेते हैं इक्विलिब्रियम इक्वेशन यूज करके, राइट?
एक्सक्यूज मी सर.
यस.
सर इसमें जो डेल्टा बी है या डेल्टा बी डैश है, ये गिवन होगी या उनको फाइंड करना होता है कंजुगेट मेथड या
आप फाइंड कर सकते हो ना.
जी सर.
तो यू शुड नो एटलीस्ट वन मेथड के इन केस आपको गिवन नहीं है, क्योंकि ये बेसिकली इस कोर्स के स्कोप में तो नहीं है डिफ्लेक्शन फाइंड करना, ये तो आप कर चुके हैं ऑलरेडी. लेकिन जस्ट इन केस के आपको कोई ऐसा कंडीशन आ जाए या एग्जाम में नहीं गिवन, तो आपको एटलीस्ट एक मेथड आना चाहिए कि आप डिफ्लेक्शन फाइंड कर लो. 3-4 मेथड बल्कि 5 मेथड शायद हमने पढ़े थे, तो उसमें से जो भी सिंपलेस्ट वन है इवन वो उसको दोबारा से रिव्यू कर लो कि आपको डिफ्लेक्शंस फाइंड करनी आती हैं उनसे.
सर लेकिन जो ओरिजिनल एग्जांपल है वो तो इनडिटरमिनेट है. अगर हमने मोमेंट एरिया मेथड या कंजुगेट बीम वाला मेथड यूज करना है
नहीं,
तो उसके लिए
आपने
हम मोमेंट एरिया डायग्राम.
ओरिजिनल मेथड ओरिजिनल बीम क्यों लगानी है? आपने ओरिजिनल बीम को डिवाइड किया है ना, तभी तो ये डेल्टा बी बना है. ओरिजिनल बीम में तो ये डेल्टा बी बनेगा ही नहीं, इस पॉइंट पे तो डिफ्लेक्शन होगी नहीं. इसको आपने जो डिवाइड किया इसका पर्पस क्या था? यही तो पर्पस था.
मतलब डिवाइड करने से
हाँ,
मतलब इस तरह डिवाइड करना है कि वो डिटरमिनेंट बन जाए.
हाँ, डिटरमिनेट बन जाए. अभी हमने ये चीज़ भी देखनी है कि मैंने इसी पॉइंट पे क्यों डिवाइड किया है. ये बी पॉइंट पे मैं इधर से भी तो एक रिएक्शन रिमूव कर सकता था.
यस सर.
ये भी था ना पॉसिबिलिटी. तो वो अभी हम नेक्स्ट क्लास में करेंगे कि अगर इधर से फॉर एग्जांपल मैं कहता हूँ मैं एक मूवमेंट निकाल देता हूँ, ठीक है, फिर इधर इस साइड पे पिन सपोर्ट हो जाएगी और इस साइड पे रोलर सपोर्ट हो जाएगी. तो इट कम्प्लीटली डिपेंड्स ऑन यू कि आप किस रिएक्शन को रिमूव करते हो, लेकिन आप जिसको भी करोगे फाइनल रिजल्ट आपके पास सेम होंगे। तो ये अब नेक्स्ट लेक्चर में देखेंगे कि अगर इधर से हम मूवमेंट रिमूव करें तब हमारे पास मेन हमारा जो फोकस होगा कि ये कंपैटिबिलिटी इक्वेशन हम ठीक लिख लें, उसके अलावा किसी चीज़ में इशू नहीं है। बाकी वही सेम प्रैक्टिस है कि आपने डिफ्लेक्शन फाइंड करनी है या इक्विलिब्रियम इक्वेशन लगा के रिएक्शन फाइंड कर लेने, राइट। Okay, there is another thing, a small concept. If you remember, हमने virtual work में एक equation पढ़ी थी, that is for the calculation of deflection, EI dx, right? So इसमें ये moment कौन सा था? This one. Yeah.
सर ये जिस पॉइंट पे डिफ्लेक्शन था उस पॉइंट पे आई थिंक
When all loads are acting on the beam, तो ये moment equation लिखते थे हम,
यस सर
ठीक है। और ये moment क्या था virtual work में?
यूनिट लोड के
One
जैसा
यूनिट लोड हो जाता था, या अगर हमने दूसरा मेथड आई जस्ट फॉरगॉट द नेम, उसमें आप सिंपल स्मॉल एम या यूनिट मूवमेंट लगा के उसकी इक्वेशन लिख लेते थे और फिर उसमें सब्स्टिट्यूट कर देते थे। अगर मैं इक्वेशन लिखना चाहूँ फ्लेक्सिबिलिटी की तो वो क्या होगी? एनीवन? अगर मैं इसी से कुछ कोरिलेट या इसी से फ्लेक्सिबिलिटी का रिलेशन निकालना चाहूँ तो व्हाट विल बी दैट? फ्लेक्सिबिलिटी की डेफिनेशन क्या होती है?
Inverse of stiffness.
इनवर्स ऑफ स्टिफनेस। स्टिफनेस क्या होती है? फोर्स पर यूनिट डिस्प्लेसमेंट।
Yes, sir.
So what is flexibility? Displacement per unit load, right? इसका इन्वर्स होगा ना, तो that will be displacement per force. So if I have this beam और let's say मैं इस पॉइंट पे फ्लेक्सिबिलिटी निकालना चाह रहा हूँ, ठीक है। और फ्लेक्सिबिलिटी मेरे पास क्या है कि जब यूनिट फोर्स लग रही हो तो उस पॉइंट पे जो डिस्प्लेसमेंट होगी दैट विल बी इक्वल टू फ्लेक्सिबिलिटी। सो आई विल अप्लाई दिस यूनिट लोड and then I will calculate this displacement, and now this displacement is equal to FBB, right? And if I want to write the equation for this flexibility, can I write it as this one? If I want to calculate this flexibility by virtual work method. So have you got this equation? That how did I write this one? You have to think, or you have to compare both these equations. This equation was actually when there was some load acting. Let's say there was a 10 kilonewton load acting, and then firstly we will write the equation of movement considering the load of 10 kilonewton, and we will have some equation in terms of x plus 2x whatever, and then in the second step you would replace this load by, for example, if you want to calculate deflection at this point, you will replace it by 1, and then you will write the equation of small m, that is x plus 3x or whatever. Then you will substitute both these equations into this one and you will get the deflection. But if you want to calculate the flexibility, now flexibility is already the displacement per unit force. So in the case of flexibility, your original beam will have a unit force acting on it. Now this is your original beam, and when you apply the flexural form, you will write the equation of movement, and then when you apply the virtual load, that is also equal to 1, okay, and then this displacement is equal to your, and this displacement over here is equal to flexibility, and then again you will write the equation of small m, and in this case, since both of these cases have one or point or unit load, and so your capital M is equal to small m, and that is why you can just slightly transform this equation or modify this equation, and you will get this m square over E into dx, and by applying this formula you can calculate the flexibility directly. So have you got this one? Is there any question? So this is it from today's lecture. I suggest you to go and read the this topic from Hibbeler book, because this topic I am using that book, and you will get some concept, but this is just the beginning. Don't just get confused, and we will be doing some numerical problems, and then these things will start to make sense. And if you have any question, you can ask me now, and probably the next class will be in physical mode, so I will meet you over there. So if there isn't any question, then this class is over.